हे जे दोन लाईट आहे ना ते कॅन्सल कर बरं. नाही नाही ते लाईट नाही सिलिंग नाही आली पाहिजे, खाली आलं पाहिजे आपलं.
का म्हटलं हे बघ एक गोष्ट सांगू का याची जी ओरिएंटेशन आहे ते लॉक आहे. आपल्याला सरळ स्ट्रीम करावं लागतं.
ठीक आहे. ओरिएंटेशन लॉक आहे म्हणजे
हे जी ओरिएंटेशन आहे ना
हां
आपल्याला सरळ याच्यात करावं लागतं. ते आडवा दिसते ते
काही नाही जाऊ दे.
सरळ कर ना.
चालू करणं गरजेचं आहे.
सुरू झालं आहे लाईव्ह सुरू झालं
झालं ना, स्टार्ट करून टाका मग.
डाउनलोड केलं तिथून झालं असं.
आणि ते काहीतरी माझं त्याला
नाही ते उडवत असं
झालं ते जाऊ चेक नको करू.
नाही 1 मिनिट थांब झाला आहे ना.
मी इकडे करू शकतो ना, याचा काहीच नाही.
मिनटं फक्त 1 मिनिट असं दिसतं.
पण तिथे क्लिअर नाही, लाईट बंद करून टाका. ठीक आहे, डन 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 डन.
Good morning, distinguished guests and participants and all my colleagues. To begin this auspicious occasion, we shall invoke the light of the wisdom and positivity. I now invite dignitaries to come forward to join us the ceremonial lighting of the lamp. I request all the dignitaries to kindly occupy their seats. good morning, esteemed guests and individuals. We begin our pre-conference workshop by paying homage to Shraddheya Baba Saheb Amte and Sadhana Kai Amte. It is a great pleasure that I welcome you all to the National Workshop on the Photoluminescence Spectroscopy and DFT. As an integral part of the International Conference on Materials and Applied Sciences for Society, March 2024, organized by Anandwan College of Science, Arts, Commerce, Anandwan, Baroda, in association with Condensed Matter Research Society, Bikaner, Rajasthan. Workshops like this set the foundation for meaningful discussions and hands-on training. The workshop will be focused on the luminescence spectroscopy and density functional theory, DFT. We are thrilled to have a gathering of esteemed professionals, academics, and students here. I would like to extend my warmest welcome to our chief guest of the pre-conference workshop, Dr. S.V. Murali, former professor and head of the Department of Physics, RTM, Nagpur University. I would like to extend my warmest welcome to Professor Manish Kumar Kashyap, Professor of School of Physical Sciences, JNU, New Delhi, India. Dr. Kaushik Kumar, Associate Professor, Department of Physics, RTM, IIT ISM, Dhanbad. President of the conference, Dr. Mrinal Kaya sir, Principal of ANC Baroda. Dr. Shaukat Shah sir, HOD Department, Head of the Department of Chemistry. Dr. Ashok Mistry sir, Head of the Department of Physics. Dr. Manu Singh Shekhawat sir and Dr. Nilesh Ugamgil sir, convener of the conference, felicitators and participants who have come together to express, explore and share knowledge on luminescence spectroscopy and DFT. Let's make this event both productive and inspiring. It's my privilege to take this opportunity to introduce and welcome our esteemed guests, facilitators of today's workshop. Dr. S.V. Murali is a former professor and the head of the Department of Physics, RTM Nagpur University. He is a retired professor. He is a life member of the Indian Physics Association, Vidarbha University Physics Teacher Association, Forum for Higher Education, Marathi Vigyan Parishad, and his research area is luminescence, solid-state lighting, radiation dosimetry. He has guided 36 PhD students. He has total 310 publications. He has total 7 patents and he has completed total 17 projects. He is a reviewer for the Elsewhere, IoT, Ballet, Springer, Electrochemical Society, RSC, and ACS Journal. I now welcome Dr. S.V. Murali with a token of love as a sapling. Our second esteemed guest, Professor Manish Kashyap sir. He is a professor in the School of Physical Science, JNU, New Delhi. He has an international collaboration with the Ames Laboratory, United States. He is Iowa State University, IAMS, United States. Michigan Technological University, Compton, United States. CTU in Prague, Prague, and University of Genoa, Italy. He has over 100 5 research papers in the reputed international journals and in national international conference facilities. He is a life member of the Indian Association of Physics Teachers, IAPT. He is the Indian Science Congress, life member of the Indian Science Congress, also a life member of the Indian Physics Association. His broad area of research is the theoretical condensed matter physics, material science, plasma physics, accelerating physics. He has guided total 8 PhD students, 1 postdoc, and currently 7 PhD students are working under his guidance. He has completed 3 research projects from UGC, BSc Serve, BSc Haryana, and ongoing 1 project from IKS scheme, AISTT. I request Dr. Mrinal Pai sir to felicitate Dr. Kashyap sir with the sapling and the memento as a token of love. Thank you. Our next guest of honor is Dr. Kaushik Kumar sir, who is the Associate Professor, Department of Physics, RTM, IIT, ISM, Dhanbad. He has published 103 journals articles. He has published 6 book chapters. He has hosted 91 conference proceedings. He has got lot of fundings and conducted many workshops under his guidance. He has a huge experience in the field of up and down conversion of the phosphors. I request Dr. Mrinal Pai sir to felicitate Dr. Kaushik Kumar sir with the sapling and the memento as a token of love. Now, the President of the conference, Dr. Mrinal Pai sir, under his guidance we are able to perform this conference. So I request Dr. Nilesh Udimge to kindly felicitate Dr. Mrinal Pai sir with the token of love and the sapling. Now I request Parki sir to felicitate Dr. Shaukat Shah sir, Head of the Department of the Chemistry of our institution, with the token of love of the sapling. Thank you, sir. Now I request Agram Madam to felicitate Dr. Ashok Mistry sir, Head of the Department of the Physics, with the sapling as a token of love. Now I request Dr. Anandwan sir to felicitate Dr. Manoj Singh Shekhawat sir, the convener of the conference, with the sapling as a token of love. Now I request Dr. Varunkar sir to felicitate Dr. Nilesh Udimge sir, the convener of the conference, with the sapling as a token of love. Thank you so much. We are honored to have their expertise and insight to guide us through the way. Their contribution in the optical ultraviolet visible luminescence field have been minimal, and we are grateful for their time and effort in making this workshop impactful. To formally inaugurate this workshop, I would like now convener of the conference, to deliver the welcome address. Let's put your hand together to welcome Dr. Nilesh Upunde to the
Very good morning, when I was present on dais. I welcome on behalf of MAS 2024 Organizing Committee to all the dignitaries present on dais and the participants for this hybrid event, hybrid workshop. So we have organized this pre-conference workshop to have discussion about the photoluminescence and the DFT, because this is the happening topic, and we are grateful to have the speaker from IIT ISM Anandwan, JNU, and again my beloved supervisor Dr. S.V. Moril sir, who has contributed a lot in this particular field. So we are eager to learn from them how we can carry out the research in this particular field. So I welcome everyone to this to this campus, and thank you everyone for joining with us. Thank you.
Thank you so much, sir, for encouraging words and setting the stage for the today's proceedings. Next, we have the privilege of hearing our esteemed chief guest, Dr. S.V. Moril, former professor and HOD of the RDM Nagpur University, who is the ocean of the knowledge. He will share insight on this conference. So, ladies and gentlemen, please kindly join me in welcoming Dr. S.V. Moril to the stage.
Friends, I am very happy to be here, and this prestigious event is organized here, so I congratulate the organizer, also principal of this college for organizing this event here, and I am sure that this will be a small beginning, and there will be more and greater things coming to this campus in the very near future. I am going to really speak on my topic later on, and already very late, so I think I will stop here and let us wait for the subsequent meeting. Back to Supriya.
Thank you so much, sir, for your inspiring words and the vision of the institution. Your insight have truly set us a powerful tone for today's workshop. And now, we proceed to the formal inauguration of the pre-conference workshop titled National Workshop on Photoluminescence Spectroscopy and DFT. I kindly request President of the conference, Dr. M.C. Kai, sir, Principal of the ANC Baroda, to deliver a ceremonial declaration of the pre-conference workshop. Let us all applaud as we mark the beginning of the significant session.
At the outset, let me pay homage to our founder secretary, Shraddha Abha and Tayambi. It was his birth anniversary 2 days back, and our founder trust, Mahabodhi Seva Samiti, is also in its 75th year of establishment. On this occasion, I welcome all of you for this pre-conference international workshop on material sciences. Honorable guests on the dais, honorable audience, it is a matter of immense pleasure for me to have all of you having deliberations here for the betterment of the society. Material science is one of the topmost research fields as of today. Right from space technology to rural technology. In every walk of life you may go, material science has its own significance. So I declare this workshop open for the day, and I hope that the talks here will certainly be helpful for the new upcoming researchers in this field of material science. I take this opportunity to thank the organizers for giving me an opportunity to interact with all of you. Thank you very much.
Thank you so much, sir. With this workshop now officially inaugurated, it's a time to dive into today's agenda. I give an overview of the workshop structure and the activities planned for the day. After the inaugural, we'll start with the session by Dr. Murray sir on the luminescence spectroscopy. Followed by that, the session will be honored by the DFT density functional theory by Manish Kashyap sir. After that, there will be a lunch. Followed by lunch, we'll have another talk by a prestigious guest of honor, Dr. Kaushik Kumar sir, on the topic upconversion phosphorus and its applications. Followed by this, there will be high tea and hands-on practice on instruments. After that, a final, we will close today's pre-conference workshop with the certificate distribution. So this is the outline of the exciting journey that awaits us today. I'm sure we are all looking forward to the session ahead. Before we move on to the workshop session, I would like to take a moment to thank everyone who has made this event possible. So to propose the vote of thanks, I call upon Madhukar sir.
Honorable dignitaries on the dais, esteemed speakers, dedicated participants, and my respected colleagues. It is with the immense pleasure that I stand here to extend my vote of thanks on behalf of the organizing committee of March 2024 of this national workshop on photoluminescence spectroscopy and DFT. As we embark on the journey of this intellectual enlightenment, enrichment, and the hands-on training, it is imperative to acknowledge the individuals whose efforts and contribution is making this program a grand success. First and foremost, let me express our profound thanks to the stalwart experts who will be sharing their profound knowledge and insights in these sessions to come. Dr. S.V. Mohari, Professor and former Head of the Department of Physics, RTM Nagpur University, for his invaluable guidance on photoluminescence spectroscopy, that is the cornerstone in understanding the material properties. Dr. Manish Kumar Kashyap, Professor at the School of Science, JNU, for his session on density functional theory, a theoretical tool indispensable for modern research in material science. Dr. Kaushik Kumar, Associate Professor at IIT ISM Dhanbad, for his session on upconversion phosphorus and their applications, a topic replete with cutting-edge advancements and potential. Your forthcoming sessions promise to illuminate the minds of the participants and catalyze their research endeavors. A special note of gratitude goes to Dr. Mrunal Kade sir, the chairperson of this workshop and the principal of Anandwan College, for steering this initiative vision and purpose. Our sincere thanks are also to Professor Ashok Mistry, Head of the Department of Physics, and to Dr. Shaukat Shah sir, Head of the Department of Chemistry, for blessing this occasion with their auspicious presence and lending their invaluable support. We are equally indebted to the conveners, Dr. Manoj Shekhawat sir and Dr. Nilesh Ugemuge sir, whose joint efforts and meticulous planning have ensured a robust foundation for this workshop. The participants, the true beneficiaries of this event, your enthusiasm and readiness to engage this academic journey inspire us to strive for excellence. Your active participation, rather online, offline, will undoubtedly shape the success of this workshop. We extend our heartfelt gratitude to the anchor of today's program for her exemplary hosting of this inaugural ceremony. Your poise, eloquence and seamless coordination have truly elevated this national level workshop. Thank you for your invaluable contribution. Lastly, I extend my heartfelt thanks to all those who have contributed directly or indirectly to the seamless organization of this program, from logistic support to the technical assistance. Your dedication deserves an unequivocal appreciation. As we commence this workshop, let us embrace this opportunity to expand our horizons, deepen our understanding, and pave the way for future innovations. May this event be a confluence of minds brimming with ideas and inspiration. Thank you all, and let us look forward to a fruitful and enlightening workshop. Thank you.
Thank you, Arun sir, for proposing a vote of thanks. With that, let us now begin the workshop session. Our facilitators are ready to guide you to an engaging and insightful experience. So thank you everyone, and let's have a fantastic workshop. So to expand our horizon and to bring our ideas, we have a catalyzer here, and he is a catalyst for young and active researchers. So we'll begin our session by the topic luminescence spectroscopy. You will be headed by the Dr. S. Wilmot, sir.
क्या लिखा है उसमें, क्या लिखा है? पहले वाले था वो जो पहले वाले थे। ओके।
Good afternoon, everybody. At the outset, I thank the organizers for inviting me here and giving the opportunity to talk to you. Actually, I am so eager to listen to Dr. Kashyap and Dr. Kaushal Kumar that I am quite tempted to cut short my talk and move on to their talks. But this topic of luminescence, is very vast. In fact, each slide I will be showing here is a topic for separate 1 hour lecture. So it's going to be only a brief summary. So please try to focus on that and try to expand on your own various aspects of that. No, I am not, this workshop in fact is about the material science applications for society. I am not going to talk on the applications of luminescence as such, because this is a workshop, but I will be talking mostly about the methodologies and the theories that students need to know while pursuing research in field of luminescence. So we begin with the definition itself, and this is very important. So in literature I am aware there are several definitions which are just the popular science things. They are not definitions. This one is the proper definition of luminescence, and it is very important for the beginners to understand this luminescence. This definition tells you what luminescence is and what luminescence is not. There are many light emitting phenomena, but all of them are not luminescence. So what is luminescence is given in this definition. So you must really know this definition by heart. And now don't be afraid of plagiarism. Don't try to change any word here. Each word has its meaning and its place. So always put this in quotes. Now the luminescent materials are also called as phosphors, and there are so many misunderstandings in the society, and especially if chemists are present, then they may call it as phosphorus. So it is not phosphorus. Remember, it is phosphor. Phosphor and phosphorus are two entirely different things. The distinguishing feature of the luminescence is that there is a time lag between excitation and emission. That is the most distinguishing feature, as opposed to, for example, atomic emission. In atomic emission, the time lag is very, very short. So we may call it almost an instantaneous. Whereas in case of luminescence, there is a time lag. And then the excitation, emission, then the difference between the excitation and emission, which is known as Stokes shift, the time lag, all these are characteristic of the phosphor. And what happens during this time lag? So that phenomena is very important. That gives you information about the luminescence segment, right? So in basic study, we want to find out what is the basic mechanism, what is going on. Applications come later, but we have to understand what is going on in between. And this knowledge is provided by various studies which we carry out during our investigations on luminescence. Now in solids, the factors which I have mentioned, excitation, emission, Stokes shift, etc., all these factors depend on temperature at which we are observing the luminescence also. And in solids, this is much more important due to interaction with phonons. In luminescence study, there are 5 parameters which we have to study. These are, of course, foremost is the intensity of luminescence, then the excitation wavelength, emission wavelength, time, and temperature. These are the 5 parameters to be studied. Usually what we do, we study the 2 parameters at a time, and remaining 3 are kept constant. Now, apart from the excitation spectrum, absorption is also important for measuring, say, quantum efficiency, which is the ratio of number of photons emitted to number of photons absorbed. And it is important to note that excitation spectrum and absorption spectrum, these can differ. Many times these 2 words are used synonymously, that excitation and absorption, but they are not synonyms. Excitation is that absorption which leads to emission. All absorption process do not necessarily lead to emission, because there are many non-radiative processes. In fact, while we pursue the luminescence, while we try to obtain good luminescence intensity, this process always has to compete with the non-radiative process. And the limitation for the intensity of luminescence is the competing non-radiative processes. And we have to minimize these processes in order to observe intense and efficient luminescence. So these measurements we can divide into 2 categories. One is called as the steady state luminescence. In steady state luminescence, excitation is continuous, and there is also continuous de-excitation. So an equilibrium is reached. That's what we call as the steady state. So under equilibrium, we get some emission, and then we can measure the emission spectrum, we can measure the excitation spectrum. These are the equilibrium processes. Another kind of measurement is the pulse excitation. So here, the excitation is not continuous, but excitation is in form of pulses. And this type of studies give us opportunity to study the dynamics. What happens during the time lag between the excitation and emission. These processes can be studied by pulse excitation. In pulse excitation itself, there are two types of measurements. One is the decay, lifetime of measurement. So for short time, we excite the luminescence, then the excitation is stopped. And how intensity decays with time. This is called as the luminescence decay of the lifetime. Another is the time resolved spectrum. This is much more sophisticated. In this case, we are not studying the integrated intensity, but we are studying entire emission spectrum at small time intervals, and this is really helpful for understanding the basic mechanism of luminescence, the dynamics of luminescence, what is happening at very short intervals. So very few places have these facilities for time resolved spectrum. Many times, it's a misnomer, people call simply the decay measurements as the time resolved. Many companies are also calling it as TRPS, but this is not in real sense time resolved photoluminescence. It is only the decay of luminescence where you are measuring the integrated intensity. In real time resolved studies, you measure entire spectrum. So in steady state luminescence, we measure emission spectrum, where what we do, we study the emission intensity as a function of emission wavelength or fixed excitation wavelength. Such spectra are called as the emission spectra. And second kind is the excitation spectra, in which emission wavelength is fixed and then excitation is scanned over a range. So we know which wavelengths are effective for studying the excitation, luminescence. Then most of the time we will be dealing with the powder samples, because single crystals are rather difficult to obtain and it's also time consuming. Also, the thin film, the hot pressed ceramics or transparent ceramics, they also need some specialized techniques. Whereas first product is always the microcrystalline powders. So in many applications, it is sufficient to have microcrystalline powders. So in this case, it is important to isolate incident light and record only the emitted. So in luminescence study, what hampers your detection limits is that both the probe is also light and the outcome, that is also a light. And so you have to detect the light on the background of incident light. That limits the detection efficiency. So you must be able to isolate the incident light. Now in case of liquids or in case of transparent solids, this is easy. The luminescence is isotropic, light is emitted in all directions. Whereas incident light is collimated, it is coming only in one direction. So what you do, you observe the luminescence in a direction which is perpendicular to the incident direction, and then you get rid of most of the incident. It is easy. But in case of powders, the opaque samples, this is not possible. Light is also coming in from same direction, and the emitted light is also in the similar plane, let us say. So the isolation becomes a bit difficult. And some artifacts may show up. This is very important. Whenever you are observing luminescence, you might get excited. Yes, I have obtained good intensity and so on. But you have to first confirm that this is not artifact and this is genuine luminescence. One of the common artifacts is what we call as the double line. You know, in most of the spectrometers, we are nowadays not using prisms, but we are using grating monochromatics. And hence, the spectrum, incident spectrum is distributed over several orders. So that we will have first order spectrum, we will have second order spectrum. We are using most of the time first order spectrum, but the second order line is also can be present, and you have to eliminate that. This is what happens, as I have shown here, that if we are not using proper filter, then we may get this artifact. You know, if I am exciting with 225 Nm, then when the photometer is set for 225, then in second order 550 Nm, that wavelength also will be present. And hence, I will get something at 550 Nm. So this is the artifact, this is not luminescence. And this intensity is very high. It will totally mask the genuine luminescence. So we have to use a proper filter to eliminate the second object. So here what we do, we use simple filters like say the polymer films or maybe a film coated with zinc oxide or gallium nitride, which will absorb all the light below 400 Nm. So this we put on the emission side if the luminescence is in the visible region, and that enables us to get rid of this artifact. There are also other types of artifacts. There For example, the gratings, the lenses we are using, they also may be luminescent. Extremely sharp for making this comment. But many times when you go to operator who is finished, then he will ask you that what is the solvent for this? He wants to dissolve that in some solvent and then take the statement. But my dear friends, solid state luminescence is totally different. It depends on the crystal structure. The moment you dissolve, crystal structure is gone, luminescence is gone, and all your efforts will go in vain. So you tell him that no, it has to be measured in order state only, and it is better to prepare our own order cells, because at some places there are many more people from say biology or chemistry and so on who are dealing with solutions or transparent materials. They may not have sample holders for the order samples. So better that we keep our own order samples and go there, and then this difficulty will be solved. So we should be ready beforehand, before going elsewhere. If you are lucky enough to have all these facilities in house, nothing like that, then sky is the limit. So we come to the photoluminescence types in inorganic solid system. One is the intrinsic luminescence. Means the luminescence we obtain because without any doping, the host material itself is giving some luminescence. This is what we mean by intrinsic luminescence. The most common one is the semiconductor luminescence. So here the transitions are from valence band to conduction band. So when electron comes back from conduction band to valence band and recombines with the hole it has left behind, then luminescence is produced. Another is exciton luminescence. In this case, the electron does not go to the conduction band. Electron is not totally free, but it is bound to the hole it has left behind. Such an entity of bound electron hole is called as exciton. And then you get exciton luminescence, but that again is without any doping. Then defect luminescence. There could be some transient defects also found, and these defects can give luminescence without doping. So these are kind of intrinsic luminescence. So many times this intrinsic luminescence is also called as the donor acceptor luminescence. Traditionally, the luminescence, inorganic luminescence is divided into two categories. One is called ZNS type. So ZNS type is essentially donor acceptor luminescence, and another is characteristic luminescence, that is known as KCL type. So while interpreting the luminescence, you have to know what type of luminescence it is. Is it donor acceptor luminescence or is it characteristic luminescence? Now most of the time we are studying the characteristic luminescence, that is traditionally called as KCL type luminescence. The thallium doped alkali halides, they were the scintillators. first scintillators was sodium iodide thallium. That's why this thallium is important, and it is considered as prototype of the characteristic luminescence. So let us now come to the intrinsic luminescence or the donor acceptor luminescence. So what are the processes going on? So I have given some references also to where you can read more details. So in this case, first step is of course the absorption of light, and then electron goes to the conduction band, leaving a hole behind. Then from the conduction band, electron doesn't return, but it is trapped at some site, which we call it the donor site. So electron goes there. Then in the next stage, the hole jumps this hole is taken up by the acceptor center. So these are first two states. And in the final state, the electron from the donor and the hole from the acceptor side, they become like to produce the luminescence. So you will find that the luminescence emission, this is characteristic of the gap between the donor and the acceptor. Whereas the excitation is characteristic of the gap between the valence band and the conduction band. So excitation spectra may give you the information about the band gap, whereas the emission spectrum gives you the donor acceptor, the difference between the donor and acceptor. Now, as opposed to that, we have got characteristic luminescence. In characteristic luminescence, the luminescence is between the localized levels. The excited stage and the ground stage, they are located on the same center. So electron is never leaving the center. It is not going to conduction. It is going from the ground state of the center to the excited but bound state. These are all the bound states. And all these states are within the band gap of the host. So these states are provided by usually what we call as the activator or the dopant ions. So this gives you the luminescence. Now we will be discussing mostly about the characteristic luminescence in this lecture. So in characteristic luminescence, we need essentially an activator, right? So that host itself is not giving luminescence, but when you dope it with certain element, then that induces luminescence in that. So these impurities or these dopants, because they are intentionally input, so we don't call them as impurity, we call them as dopants. These dopants are called as activators. They activate the luminescence inside that host. So they are categorized in various types. Now, these various types, why we categorize them? Because accordingly we can interpret, and lots of experimental studies have already been done. We know which theories to be applied, what is the language to be used, accepted theories for such type of luminescence. So we talk in that language, so everybody understands what we are talking about. So these activators are called as NS2. NS2 means they are having 2 s electrons in the last orbit of that activity. So hence they are called as the NS2. So there could be 4s2, 5s2, 6s2 and so on. The typical examples are thallium plus or PB2 plus or Bi3 plus. Then there are some activators from the third row transition elements from scandium to zinc. So they are having incomplete D shape. So they are known as the 3D transition elements. From scandium to zinc, of course scandium and zinc, they will not produce any luminescence. Only because they will have 0 and 10 number of electrons. So they will have either complete incomplete shell or fully complete shell. So the examples are say copper plus Rn2 plus, Cr3 plus. These are very commonly studied luminescence because these activators produce luminescence in the visible region, and the instrumentation is quite economic and commonly available for visible luminescence. Other activators may produce luminescence in the infrared region. Then there are the activators in the next transition element. These are the lanthanides or the 4F transition elements. So they also are very good activators. Then there are certain molecular ions. So these ions also are grouped. They also produce luminescence. They are vanadates, tungstates, neobates, uranates, and so on. So here it is not a single ion, but it is a molecule, entire molecular ion that produces luminescence. So different kind of theory, mostly the molecular orbital theory has to be invoked. So I have briefly shown them in the periodic table. So these are the 3D transitions elements. Then here we have got the NS2 elements. In fact, antimony also comes under NS2 because antimony has got two valences. Antimony 5 plus and antimony 3 plus. So 3 plus I think it comes under NS2 category. And then of course lanthanides will be here. So they occupy similar square on the periodic table. So if it is expanded below, then you will see all the elements from lanthanum to mutation. So first we come to NS2 activators. So there is a general method for describing and interpreting the luminescence due to NS2 activators. So here electronic configuration in last shell is with 2 electrons. So the familiar examples of thallium plus or lead 2 plus or bismuth 3 plus, this is the electronic configuration. So here you will see there are 2 electrons in the 6th orbit. Now ground state configuration is 6s2. So here you have got 2 electrons in the s orbit. So total spin is 0 because the electrons are anti-parallel. So since the total spin is 0, there is only one state which is written as the singlet state, that is 1s2. Again, while we are talking about singlet etc., let me again give you sort of warning or a caution that if you read about organic luminescence, then they talk about the singlet and triplet and Jablonski diagram and so on and so forth. This is not at all applicable to the inorganic luminescence. In inorganic luminescence, we are not dealing only with singlet and triplet. There are doublet, quartet and so on and so on. Right? So let us be worried about that. I have seen many good review articles with the title luminescence in inorganic tungstates or luminescence in inorganic this that, and under that title entire description was that of the organism. So let us be worried of the literature also and especially mistakes in the literature. So don't go by everything that is printed. I mean, I find it very difficult, while trying to explain it to my students. When I am trying to explain it to students, they say, but sir, this is written in the journal. But sir, it is written in the journal with impact factor 29. So how can that be wrong? So that can also be wrong. Let me try to convince you. Then excited state configuration is when the electron jumps from the this s orbital to the p orbital. So the configuration is now one electron is in s orbital, one electron is in the p orbital. Now here two possibilities are there, that electrons can have parallel spin or electrons can have anti-parallel spins. So we find that when the spins are parallel, then total spin is 1. If total spin is 1, then we can have the J values from L plus 1 to L minus 1 at the interval of unity. So there can be 3 states, right? So that the J values can be 2, 1 or 0, because since we are dealing with the p orbit. The total angular momentum for s orbital it is 0, for l orbital it is 1. So total orbital angular momentum is 1. So we can get the states like this, 3p2, 3p1 and 3p0. In j equal to 2, j equal to 1, j equal to 0. These three states are possible. And for the anti-parallel spins, s is equal to 0. So then we have got a singlet state which is denoted as 1p1. So in all there are 4 states. 3p2, all helium, lead, bismuth, all these can be described by this general formality. So I will request the organizer also to give you. So now this type of energy, simplified energy, it will go in vacuum ultraviolet. It will go in vacuum ultraviolet. Find this. Then and this is by the spin orbit coupling or by hadronic coupling. One is 0 to 3p1 and one is 0 to 3p2. These transitions, though they are weaker, but they are of practical importance because they are at lower energy and most often we observe these transitions. So once the electron reaches these levels, then it will relax. This relaxation is what introduces the time lag, and this qualifies the process for fluid to be categorized as luminescence. So from here it will finally come to this state, 3p0. So we find that there will be some photons created in between, and then we will get emission when the electron returns to the ground state 1s. Then we come to 3D activators, and we may have enough time only to discuss today 3D activators. So these are, I explained earlier, these are third order transition elements from scandium to G. Now, this is electronic configuration. There are 8 electrons in the D shape, and the D shape starts spinning. I mean, before D shape is completed, the 4s shell is filled because energy-wise they are quite close. Now, what is the result of this incomplete D shape? That all the transition elements, they will show multiple valences. They can have various valences. For titanium can be divalent, trivalent or tetravalent. So we are using these dopants. You have to know in what valency the dopant exists. So whether it is divalent, trivalent or tetravalent. So characteristically different luminescence is obtained depending on the valency. Also, in US may trouble you that to identify the valency, then you can use more sophisticated things like X-ray photoelectron spectroscopy and so on. So that will tell you about the valency. And again, our chemist friend may advise you that you choose the starting dopant as divalent and then it will go as divalent, or start with tetravalent and it will go as tetravalent. But unfortunately, this does not work practically. So the starting valency could be different, and inside the crystal there are so many possibilities, because it can give electron or borrow electron. After all, dopants are in very small concentration. For example, TiO2, we know that it is the tetravalent state, and it might be difficult to get other states. But once you go titanium in the crystal, where various possibilities are there. Divalent is also possible even if you are looking TiO2, because some electrons may be shared with something else. So otherwise, it will not be possible to draw divalent because of European soil. It is always trivalent. But even if we go starting material is trivalent, You may go as diamond, or you can use some reducing techniques, etc., and convert it into diamond. Don't try to find out diamond minimum component. That will be difficult to find out, that will be costly, that may not be stable. So stable balancing for most of the lantern MCQ, 3. These the transition elements, they are more flexible perhaps, because you get compounds with various frequencies. Vanadium exists with trivalent of pentavalent states, chromium in 2, 3, 4, 6. So we have also got Cr2, we also have got Cr3. But we have used Cr3 zero soluble in nitric acid and so on and so forth, then we will get Cr3, no problem. Magnet is wonderfully liquid. It exists in all 7 valencies from 1 to 7. So that makes our job more difficult. But most common states, valence states of manganese as far as luminescence is concerned is 2 and 4. So you can have luminescence from divalent manganese or tetravalent. Then FeCO(N)R, they exist in divalent or trivalent. Now these FeCO(N)R, they are being luminescence in the infrared range. Now copper also exists as copper plus and copper 2 plus. So copper 2 plus also sometimes some semiconducting compounds are formed. So it can also result in the donor acceptor pair type of luminescence. So in many semiconductors, for example in ZNS, you may not observe the characteristic luminescence of copper, but you will get the donor acceptor pair luminescence. Whereas if you do copper plus in KCl, you get characteristic luminescence. So copper is a really a wonderful actuator in that sense. In that it can exhibit both type of luminescence, the donor acceptor as well as the characteristic. Now we are going into something deeper into theory, and it will make your head a bit stream a bit. So for the next 10-15 minutes, don't get discouraged if you are not understanding it. This with references and this PPT will be with you, so you will have to go again and again through these papers and understand. In fact, it's not all that difficult. Let me not discourage or frighten you. It's the nomenclature and the terminology, the notations. Notations, if you are not familiar with the notations, then we get stuck up at the first place. But you can go back to your 10th or 12th class and understand the Bose theory and what are the 4 quantum numbers SBDF, with orbital angular momentum, spin angular momentum, total angular momentum. So if you know your quantum number LSJ, then the rest of the things will follow. Then it is not all that difficult. So this theory was given as way back 1929. So that will give you some confidence. That if somebody has done it in 1929, and if I am completing my PhD in 2029, then it should be quite simple for me after a gap of 100 years. And then we formulated the basic ideas of crystal grid theory. So crystal grid theory is basic way of understanding the luminescence of 3D type of activities. Then there is a semi-empirical approach. So after going through the important states of these theories, we come to the results. And these results can be generalized. So the luminescence of all 3D and type of activators can be described by what are known as Tanabe-Sugano energy level diagrams. And when I was born, at that time this theory was given, all these energy levels were calculated, and they are available to us. All these Tanabe-Sugano diagrams are available to us. So if I am using one of the 3D elements as activator, all those diagrams are there. What qualitatively we know what it will look like. What changes is your host. Your host will quantitatively change. Qualitatively the diagram remains the same. So for example, if we take now Mn4 plus as an activator. So in this case, 4F is the ground current. and then there are various other terms. So we start with the free ion levels. So we don't bother about the crystal. So we can calculate from the atomic spectra what are the energy terms for every purpose. So that also is a bit complicated because there are now 4 electrons. It is not 1 electron system like hydrogen. It is not all that simple. There are 4 electrons, and then there can be each electron can have spin up or down. So we can have different types of energy levels. So there are 120 possibilities to distribute these 3 d electrons through 10 allowed states in 5d orbitals. And then there are, for free ions, there are LS terms. These are all, the notations are 4p, 2p, 2d, 2d, 2h, 2g, 2h, etc. So 8 such terms are possible. Then all these terms are degenerate because they are having same energy. So unless there is some external field applied, they will all have same energy. And this external field is now in terms of crystal. When this ion is put in crystal, then it experiences crystal field. So these terms split into number of levels. Now these crystal field configurations, they are denoted by some 4 terms. So these are notations coming from molecular orbital theory and the group theory to be used for the calculations. So these are termed as T3, T2, T2 and T3. These are just notations, don't get frightened about them. And these energies are measured in terms of dq. I will tell you why it is measured in terms of dq later on. So crystal field is measured not in absolute terms, but it is measured in units of dq. dq is the crystal field strength. So what are the Tanabe-Sugano diagram? These are simply the energy level diagram in terms of dq, field strength. So these energy level diagrams, these are not one-dimensional energy level diagrams as for free ions. In free ions, you know the state and then it has got the energy. Here, energy also depends on the what we call as the configuration coordinate, or how this what are the ligands, right? What are the surrounding ions of 3D ion, and how much is the bond length and so on and so on. So it's really a 2-dimensional graph. So you have got the energy on one axis, and also on the other axis you have got the configuration coordinate, or in this case we put crystal field as a second parameter. Now this crystal field of course depends on what are the ligands and how close they are, how many in number they are, and so on and so forth. So all this is summarized in one parameter, that is crystal field. Now these energy levels, they are expressed as function of crystal field strength and some parameters of the theory. These parameters are called as the Raka parameters. Now these states are labeled by irreducible representation of the point group related to the symmetry of the crystal field. So this will depend on your host. Now this may look at first a bit complicated, but I will tell you semi-empirical measure also, how to calculate it from experiments. That will become easy. So in case of octahedral symmetry, we are having the states. This ground state is say 2s plus 1 Ag, 2s plus 1 A2G and so on, then Eg and T. So 3 types of levels basically. They are A1G, A2G, then they are T1G, T2G and Eg. So these 3 types of levels are there. Why we are categorizing them? Because their behavior under crystal field is different, and this decides the property, luminescence properties. So in all these cases, this 4A2G is the minimum energy state. This is called as the ground state, and this is constructed from the d electrons occupying the orbitals, and they have parallel spins. Then the energy is minimum. In anti-parallel spins, of course, the energy will be higher perhaps. So basically we have to remember three states. Excited states are derived from 2E, 2P and 4P states. A states decide the ground state. There are three types of excited state, 2E, 2P and 4P. Now of these, the 2A and 2P levels, they do not depend much on the crystal field. So they remain almost the same. The variation is very slow. But these 4P states, this will depend, this will show huge variation with the crystal field. And for this reason, we find that the various levels, they depend, 4P states, they vary from host to host, depending on the strength of the crystal. And the crystal field itself depends on what sort of anions. For example, if you have tungstate, it will be different. If you have vanadate, it is different. If you have only oxide, it will be different. So depending on what host you are studying, and also the crystal structure, what is the bond length. So excitation is from the ground state core A to G to the core T to G. Then relaxation depends on the states 2P and 2P. Emission will not be from 4P. So then it will relax to say the T1 states. And then emission is either from 4P2 state or from 2E state. So which state is lower? If 2E state is lower, emission is from 2E state, and if 4P2 state is lower, the emission is from 4P2 state. The relative position depends on crystal field or the parameter dq. Now, for the weak field case, this 4T2 that lies below 2E and the transition is allowed. If it is allowed, intensity is high and the lifetime is short. Lifetime is in the microsecond. So for the 3D transition element, we can get two types of luminescence. One is the broadband luminescence, which is allowed, intense, and its lifetime is microsecond. In the high field, the reverse is the situation. 2E states is low, 4P state is higher. So electron will relax to the lowest excited state, which is 2E state. Now this is actually forbidden, and the emission is in form of sharp line. The lifetime is of the order of milliseconds. So we have to distinguish two types of luminescence. One is the broadband luminescence, another is the sharp line luminescence. If it is sharp line, lifetime is milliseconds, and it is from the 2E state. And if it is broadband, then it is from the 4T level, and the lifetime is microseconds. So these two facts we know from the experimental measurements, whether it is broadband or whether it is sharp. So you don't have to calculate, but from these features itself you know what type of luminescence it is. So this 2E, 4A, 2G transition is really forbidden. It is only allowed in the crystal because of the spin orbit mixing or sometimes by the hadronic transitions and so on and so on. Now this is so-called the Navier-Stokes diagram, energy diagram. So as opposed to the atomic or free ion levels, in case of atomic we have got three straight lines. Energy is not a function of, there is no other parameter. If you have got hydrogen energy levels, they are more or less absolute, they do not change. But here, it depends on the crystal field. Once you put this 3D ion inside a crystal, then all levels change. They do not have the free, these are the free ion values. On this axis, they are free ion values. What happens? Once you put them inside the crystal, all levels will change. Most of the levels will go down. And depending on the crystal field strength. So we find here that if crystal field strength is small, right, then we find that this T level is below the P level. So there will be absorption to higher levels, electron will relax. It will come to maybe T1 level or 2T1 level, and from there you will get the emission. So this emission is brought back and allowed, and lifetime is microseconds. But if field strength is high, then T levels are at higher elevation. And we will find that E level is at lower elevation. So from 2T2 or 4T2, electron will relax to 2E level and emission will be from 2E level. And you will get sharp line emissions. Now there are various theories, or semi-empirical methods. I will skip this. Same thing, in reality the diagram is more complicated because it is a parabola, it is not just a straight line. But each energy level is a parabola. Now simplified diagram is like this. That in big field, the T levels are higher, E level is lower, and then you will get, in the big field, this 4T2 is the lowest level, and the emission is from that level in form of broad band with microsecond line. For strong field, all T levels are above E level. 2E level is the lowest energy level, so emission is from 2E level. It is in form of sharp line and lifetime in millisecond. It is a forbidden process. Now, the terms weak and strong, these are relative. So, we go really by this. That if we get the sharp line, then we say crystal field is weak. And if we get, if we get sharp line, then this field is strong. And if we get broad line, then this is really weak. So from experimentally or phenomenologically, then we can find what type of limitations we are dealing with. Now energy layer diagrams of other 3D3R similar to Mn4 plus we are having vanadium 2 plus. That also has a 3 electrons in the d orbital. Cr3 plus again same thing, Fe5 plus again 7. However, the characteristic features are different because of the charges. Mn has got 4 charge, Rn has got 5 charge, vanadium has got only 2, Cr has got only 3. And we know simple electrostatic law, right? What is the force of electrostatic interaction? Q1 Q2 upon R square. So if here Q is high, right? For Mn it is 4 positively charged. Fe5 plus 5 positive charges. So naturally the force will be stronger. For a given distance, the force is stronger because there is force of 5 charges. Whereas for vanadium there are only 2 charges. So in general we will find that for vanadium 2 plus the field will be weak and we will get band emission. For Cr3 plus the field is intermediate. So in some cases if distances are shorter, R square if R is short, then force is large and we get line emission. If R is large, then force is small and we will get the band emission. So that is for Cr3. For Mn4 plus and Fe plus, usually we get strong field and line emission. The band emission is rare in this case. Now, how to calculate it from theory? So from theory point of view, we can calculate all these things. So these are known as Raka parameters. So these are, you can say, calculated as well as from experimental measurement also you can find out the Raka parameters. So it becomes in a sense semi-empirical theory. So either you obtain parameters from the experimental measurement. So it is a bridge between the theory, the crystal field theory and the experimental measurements. So this bridge is provided by Raka parameters. So the integrals here, these are called as the Slater integrals. So there are various orders. K will take various values, the 0, 2, 4 and so on. So all these parameters A, B, C are called as Raka parameters. They are related to Slater integrals. From theory, you can calculate values of A, B, C. These are the Raka parameters. Now parameter A is not important because it is same for all the levels. So it only changes. So when you calculate the emission or absorption, it is the difference between two energy levels. So the term in A will get eliminated. It is same for all of them. It is the terms in B and C which are important for the luminescence measurements and their interpretation. So you will find that all the terms, earlier I had shown, isn't it? The 8 terms for ML4 plus or PL plus CR3 plus. So all these 8 terms can be calculated from 2 parameters only, B and C. So from 8, we come to the calculation of 2, B and C. So that will make you rather friendly with the Raka parameters. So integrals could be rather awe-inspiring and you get frightened, but there is some sort of consolation here that you have to calculate only 2 parameters B and C, and all 8 levels are then calculated. So you know all the transitions, what will be the excitations, what will be the emissions, everything you know once you know parameters B and C. And on the contrary, if you have got experimental results first and then you want to back calculate, then you will not go to the integrals and so on. You don't need to your experimental results, and then you can calculate. So these are the experimental results. Now these are not the energy levels, these are the difference from the ground state. Ground state is 4A to G. So this is the difference between 4P to G and 4A to G. So this is the position. So you will get usually 2 excitation bands, and from these 2 excitation bands, the difference between 2, you will get the difference between 4P to G and 4P1 G, right? From the emission, you will get the difference between 2 EG level and 4A to G. So just from these 3, we get 3 measurements. The difference between 4T to 4A to G, 4T1 G, 4A to G, and difference between 2 EG and 4. So from experimental measurements, we get 3 quantities. These 3 quantities then are related to the crystal free strength. So we define a parameter x which is given by 4A to G minus 4T1 G. What is 4A to G minus 4T1 G? This is 4, the difference from 4T1 G minus 4A to G. This difference is 4T to G minus 4A to G. So from this we get the parameter dq, right? So dq is this numerator. Then the Raka parameter b is given by this. dq upon b is this. So first you obtain dq from experimental measurement, then b is obtained from this equation. Once you obtain b, you can obtain c from this equation. So b and c. So basically there are 2 measurements, right? 3 measurements, 2E, 4T2 and 4T1. From this you calculate B and C. When you calculate B and C, you calculate all 8 energy terms. So once you calculate the Raka parameters, it becomes as simple as. So Raka parameters is the standard method of analysis of the emissions from 3D activities. Now, we can summarize what is the effect of crystal field. We say that the Raka parameter change from there we have it. So, what is the effect of crystal field? Effect of crystal field is to change the Raka parameter. And we can bring in some chemistry also here. So, these parameters B and C, we are defined in terms of the Slater integrals. So, it gives us, provides us some insight. These are combinations of integrals representing the Coulomb repulsion and exchange interaction. Now, exchange interaction has really no parallel with classical physics as such. It's a purely quantum effect. So, what is the exchange interaction between pairs of electrons? And then values of B and C are decided by the competition between ionicity and covalency. So, it is here where our chemist friends can help us, So, looking at the host, they can tell you these are 2 extreme cases, that ionic bond and the covalent. Ionic bond is found when electron is totally donated to the neighboring element, it forms ionic bond. Whereas covalent bond is found when we have a sharing, the electron is shared and so on. So, these are the extreme cases. In reality, it is neither purely ionic nor purely covalent, but you call it as this much percent of ionic. I hope it is correct. we call that, yes, ionicity is so much percentage and so on. So by looking at the host, your chemist friend can advise you, yes, you can expect that this is a more of a covalent type of body. So what type of changes in the Raka parameter you can expect. So covalency leads to the smaller values of B and C, whereas ionic type will lead to larger values of B and C. So now once we are armed with these tools, we know what to expect, right? So we know our host, we know what ion we are putting in, then what type of effect is expected. So we not totally blind, but we know what type of effect is expected. And then accordingly we look for, we also know what type of lifetime is expected. So if you have a bad type of emission, lifetime is of microsecond, then we know xenon flash time to be used in the experimental setup. If it is sharp line, then lifetime is millisecond, and simple chopper, mechanical chopper will do the job. So you know all this information beforehand. You are not going there blindly, right? So that when asks you question, then you can say, yes, a priori, I know this is. So that is the beauty of analysis or physical reasoning, chemical reasoning of the process of luminescence. I think I'm looking for this. Each slide will be a topic for a separate overall lecture. Next, in fact, we have to consider lanthanides. So these are the lanthanides. And it's quite interesting, to go into lanthanides also. But let us see if we take time sometime in these components or later on, then we will discuss the lanthanides. Actually, I am as eager as you to listen to Dr. Kashyap. I think it is his lecture next on DFT. So thank you very much for the question.
Thank you so much, sir, for sharing your so profound knowledge with us. And we are very thankful for the opportunity you have given us from your extensive experience and knowledge and insight you have shared us with today. So it's a time for the session by Dr. Professor Manish Kumar Kashyap sir on a density functional theory, and as we are very eager to listen to you, sir, so please join us here for the next session.
Yeah.